The White Bay area is full of untapped potential, surrounded by neighbourhoods of high socio-economic status and located nearby the Sydney Central Business District, suggesting that it is a prime location for a commercial and potentially a tourist centre. When exploring the area in Tableau using 2016 Australian census data, the high spending potential of the area is accentuated by the high incomes of nearby residents and relatively low associated living costs, which can be seen in comparing these weekly rent and weekly income graphs. However, the highest population concentrations are located in Sydney Haymarket and Pyrmont Ultimo, but these individuals do not yet have reason to cross the Anzac Bridge into adjacent areas. A commercial centre will change this behaviour and likely also entice tourists visiting the central business district to visit. Moreover, Lilyfield Rozelle displays the lowest population distribution, despite occupying the third largest land area, which is seen through both the population graph and distribution of SA1 areas, adding credence to the idea of residential high-rises as well as commercial high-rises in order to utilise this previously vacant land. Keeping this mixed need for residential and commercial space in mind, the assignment 2 iteration of the Grasshopper 3D model combined waterfront stores, a large shopping area, a waterside park, and a mixture of residential and commercial high-rises to create an ideal commercial centre to cater to the needs of the surrounding demographic. However, what this model wasn't suited to is the iterative process needed for the later stages of the project, as it used a list item method to separate out each of the 5 areas. This meant that if I changed any of the initial parameters, the park may end up occupying a different plot as its item index also changed. This rule applied for any of the other buildings in the area as well. My solution for the model used in creating the machine learning dataset was to assign the park and shopping centre plots based on, respectively, the largest and second largest plot areas. Every other building was treated as a collective, and this allowed me to change the input parameters without fearing that the outputted 3D model would have ridiculous features. The created dataset includes 5 inputs and 5 outputs, the former of which were created by assigning a series to each individually and linking these to a tree branch attached to the loop. The inputs included the minimum road length, parcel depth, parcel width, the plot split rate, and a building height multiplier that was part of the attraction script for building height within the 3D model. And the outputs were the total volume of all buildings within the 3D model, the total amount of hours spent in the sunlight for these buildings, the area of all the parcels combined, the number of buildings within the model, and the area of the isovist analysis. I then imported this dataset into H2O to run the AutoML model generator, where my primary problem seemed to be the lack of memory space in my computer. And after several instances of what should have been 50-minute models failing after 5 to 6 hours, I generated 3 separate models that used the previously stated inputs to predict the volume, parcel area, and sunlight hours of the Rhino model. All AutoML models were generated using a CSV file and a split of 0.85 to 0.15. And the top models were used in all except for the volume AutoML model, as the first 2 extended vertically into infinity and only the third one turned out to be of use, as it is seen here. However, before moving on to Tableau, I delved into sklearn to look at the confusion matrices generated by my data, and the associated k-means scatterplot graphs. One of the first things I noticed was that, when reading the CSV file, there was a volume outlier generated on row 273 of the graph. After deeming it to be a true outlier rather than a golden perfect model that was generated by fluke, which was done by both looking at it in Grasshopper and comparing sklearn graphs, I manually removed it from the dataset. I then moved on to assign each volume value as either bad, good, or very good, depending on how high its associated volume was, with the assumption that a certain volume would be needed to accommodate the expected population that would be visiting the White Bay precinct. You can see the distribution of these groupings by row count in this graph. I then dropped the output columns from the dataset so that I could begin testing against the classifier column that contained the good and bad groupings. Looking at the confusion matrices, there is an unbelievably high precision, with the lowest displaying a 95% accuracy, and when I decrease the test split size to 0.8 from 0.9, this perceived accuracy increases. The primary outcome that I gain from this is that a larger dataset is needed to decide on the most accurate model using this method. However, with a dataset of 400 rows and 10 columns, it wasn't possible to increase the inputs without making the Rhino model grossly out of proportion and therefore unusable. Moving on to the k-means graphing, the trend lines and relationships between inputs and outputs can be easily visualized using this method. However, I also found the relationships between different outputs to shed some light on how they can be manipulated to locate the ideal scenario. Using a second database that I copied earlier in the code, I normalized the outputted data using the min-max scaler included in sklearn, and used this to generate clusters and cluster centers for graphing. The normalization was needed to ensure accurate clustering, without which the clusters would only take into account one of the axes values, rather than both. I then reformatted the data into 5 separate groups and scatterplotted them, along with their centroids. This first graph shows a generally inverse relationship between the volume and parcel area, with some outlier groups. This is likely due to how my height multiplier loop worked, as it decreased the overall height of the buildings as other values such as parcel depth and width increased. Far more interesting is the volume and sunlight hours graph that was generated in the same way. This distinct downward trend shows that as volume decreases, sunlight hours increases, which is to be expected as a taller or wider building will cast a larger shadow than a small one. Finally, the sunlight hours parcel area graph shows the opposite, an upwards trend as parcel area increases, the sunlight exposure does as well. Once again, we see the building height input at work. Coming to the final Tableau dashboard, the 3 sklearn graphs are situated beside the 3 AutoML model outputs. An example of the shifting parameters may be seen here. The intention of placing the graphs on the dashboard is to impart knowledge on how changing certain inputs affects all 3 factors based on which ones increase or decrease each shift. Furthermore, by maximizing each output, such as sunlight within the parkland area, the best and most hospitable commercial center may be constructed for the White Bay precinct.